Right, so looking at example 3.2, we're asked to calculate the entropy change. So in other words, we're looking at calculating delta S for a perfect gas. If the volume occupied by 1 mole, so we're giving some information regarding that, of these gas molecules is doubled at any constant temperature. So in other words, we're also given that the change in temperature is 0. Right. And then in the notes, you see that I do the calculation, but essentially where it comes from is the section just before that. So section 3.4.1, which is the isothermal expansion of an ideal gas, and then more specifically equation 3.4, which states that delta S is equal to nR ln of Vf over Vi. So thinking of that equation, so in other words, because we have a perfect gas which is expanding isothermally, because that is what the constant temperature means. So I mean, constant temperature means isothermally, which we discussed. So it's the isothermal expansion of an ideal gas. And basically we're given the volume occupied by 1 mole of these molecules is doubled. So that gives us this then. So in other words, the ratio between the final and the initial volumes is 2, because I mean it doubles, so double means 2. And then we're also given the number of moles. So we have everything that we require in this equation, because we have that, and of course R is a constant. So then you just basically calculate it as I've done it in the notes. And then a very important point that I want to highlight is that you need to understand that this is now what we've calculated for the gas. So for the gas's expansion. In other words, this is for the system. And it's not something for the surroundings. We have no information knowing what kind of heat exchange was there with the surroundings and what was the effect of the changes on the surroundings. That's actually discussed in the next section. So this is purely a focus on the system. So in terms of, for example, this would be in your glass bulb, so that you have in your glass bulb that we have, for example, in figure 3.1a, we have those two glass bulbs. Remember, something like that. And then we had the tap there, but then eventually the gas occupies both sides. The typical doubling of the two chambers, or the doubling of the volume. And we can see that it is indeed spontaneous, because we have a positive value for entropy, because it increases. The entropy increases, so in other words, it is an indication of what? An increase in the disorder, because I mean a positive delta S, so delta S in this case is larger than 0, so in other words, it means we have an increase in disorder. Right, so, and of course, increase in disorder means that it will happen spontaneously, as we expect with our glass bulb example. Okay, so this is a very nice example in terms of like something very simple, but you can actually, the understanding and the discussion behind it is much more valuable for your understanding of it. So in terms of what does this delta S value mean, what does the system actually mean in terms of, is this something that we expect will happen spontaneously, whatnot. But once again, we've only looked at a system. We haven't looked at what happens with the whole universe, right? Which is something we'll get to in the following examples. Okay, just a final note. In terms of the units, so you note the units for delta S is joule per Kelvin. And then for the molar entropy, it will of course be joule per Kelvin per mole, right? And of course you need to match your R value constant to the right units. So in other words, if you were given something which wasn't in mole or whatever, then you needed to match that into the correct units. All right. So just be cognizant of that, whether or not you're always asked to calculate the molar entropy or the entropy, then you know which units you need to work in. Okay.